Everything we rely on today, your phone, your computer, even your car, it all runs on tiny little semiconductor chips. But have you ever stopped to wonder how they actually work? For a really long time, even the brilliant minds inventing this stuff were totally stumped by one single fundamental problem.
Think about it. How do you possibly measure and control something you can't even see while it's moving through a solid object? That was the question in the early days of electronics. And the answer was going to change absolutely everything.
So people knew these materials were special. They knew you could kind of coax electricity to flow through them. But what was really going on inside? How fast were the charges moving? How long did they even last? Without those answers, trying to build reliable electronics was like trying to build a skyscraper without a blueprint. It was just a complete black box.
So, to crack this thing open, scientists first had to really wrap their heads around the puzzle itself. What exactly is a semiconductor, and what makes it so darn special?
Okay, so a semiconductor, like the name kind of suggests, is a material that's basically halfway between a conductor, think copper, where electricity flows freely, and an insulator, like glass, which blocks it completely. And it's this in-between Goldilocks property that makes it so incredibly powerful.
And here's the magic word: control. In a conductor, like a copper wire, electrons just go for it. They flow. In an insulator, they don't flow at all. But in a semiconductor, you can actually control that flow with incredible precision. And, of course, to control it, you first have to understand it.
Which brings us right back to that big central puzzle. You've got these tiny little charge carriers, electrons, zipping around inside a solid chunk of silicon. How in the world do you measure their speed or their lifespan? It's not like you can just peek inside and time them with a stopwatch. And to make things just a little more complicated, it's not just about the electrons themselves.
Yeah, this is where we get to the really cool, kind of mind-bending concept of electron holes. So imagine a pipe that's totally full of water. It's packed. If you tilt it, nothing really happens, right? There's no room for the water to flow. But what if you take out just one drop of water? Suddenly, you've created a bubble. Now when you tilt the pipe, that bubble starts moving. It looks like a real thing traveling through the pipe. Well, that bubble is exactly like an electron hole. It's the absence of an electron. And in a semiconductor, it turns out it's way easier to track the movement of that one single bubble than it is to track all the countless water drops moving around it.
So, how did they do it? How did they finally measure the movement of these invisible electrons and these weird holes? The answer, it turns out, came from a brilliantly, almost ridiculously simple experiment.
This is the key analogy that makes it all click. Imagine a murky river. You can't see the individual water molecules moving, right? But if you drop in a pulse of bright red dye, suddenly you can see everything. You can see how fast the current is moving, you can see how much the dye spreads out, and you can see how long it takes to fade away.
Well, this is precisely what two scientists at Bell Labs, J.R. Haynes and William Shockley, did. But instead of putting dye in a river, they injected a pulse of charge carriers, those electron holes, into a piece of semiconductor and just watched what happened. The whole setup was just so elegant. They took a block of semiconductor, they applied a voltage to get things flowing, that's their river current, then at one end, bam, they hit it with a sharp pulse of extra holes, that was their drop of dye. And on the other end, they had a detector, just waiting, watching for that pulse to finally arrive and ready to measure exactly how long its journey took and what it looked like when it got there.
And the results from this simple little setup, they were nothing short of revolutionary. This is what finally opened that black box for good.
So the underlying quantum physics, all the really complex math, predicted that this pulse of holes should move through the material as a sort of drifting, spreading out bell curve. And when Haynes and Shockley ran their experiment, the signal that popped up on their detector was, you guessed it, a perfect match. It was beautiful. Theory and reality just lined up perfectly.
Okay, now this equation looks pretty intimidating, I get it, but you do not need to be a physicist to see how cool this is. This equation is basically the mathematical recipe for that pulse of dye in their semiconductor river. It tells you exactly how the carriers drift, how they spread out, and how they eventually disappear. And the most important part is that it's packed with variables you can actually measure, variables that would become the absolute cornerstone of all modern electronics.
From that one single experiment, they could pull out 3 golden numbers. First up, mobility. That's basically the speed limit for the charge carriers. It tells you the absolute top speed your chip can ever run at. Second, lifetime. This is how long a charge carrier can survive before it vanishes.
This is super important because it determines how long a bit of information, a 1 or a 0, can exist. And third, diffusion. This measures how much that pulse of charge spreads out, and that directly affects how tiny and how close together you can pack all the components on a chip.
And this is the whole point. For the very first time, this wasn't guesswork anymore. Scientists now had a reliable, repeatable way to get the hard numbers they needed to engineer things. They finally had the rules of the road for electricity inside a solid. And once you have the rules, everything changes. This is the moment physics starts to become engineering. And things moved fast. I mean, incredibly fast. The experiment happens in 1948. A year later, in 49, the paper detailing all the results is published for the world to see. And by the early 1950s, this data is the engineering bedrock being used to design and build the very first reliable transistors.
This was the title of the paper that laid it all out. Now, I know, it doesn't exactly sound like the most exciting beach read, but those two words, quantitative studies, that was the bombshell. It meant they had the numbers, they had the data, they had the blueprint.
You see, the Haynes-Shockley experiment wasn't just some clever physics demo in a lab. It gave engineers the essential numbers they were desperate for: mobility, lifetime, diffusion. It gave them the blueprint they needed to build the transistor, and by extension, well, to engineer the entire digital world we live in today.
It really makes you wonder, doesn't it? The solution to one of the biggest technological puzzles of the 20th century wasn't some huge, complicated machine. It was just a really elegant idea. Hey, let's put a little dye in the river and see what happens. It kind of leaves you with this thought: what other invisible puzzles are all around us right now, just waiting for their own clever, simple experiment to come along and unlock another revolution?